Hi, my name is Dowlette Alam El Din, and the name of my project is High Resolution Functional Mapping of Cortical Dynamics in a Parkinson's Disease Mouse Model. So a little bit about myself to start off. I'm going to be a senior this fall at the University at Buffalo in New York. My major is biomedical engineering, and I will be graduating in May 2020 with a Bachelor's of Science degree. This summer, I have been conducting research at the University of Florida with the SURF program. SURF stands for Summer Undergraduate Research at Florida. This program has taught me about graduate school and what life is like as a graduate student. I've had the amazing opportunity to spend my summer working in the OAS lab and the Electrical and Computer Engineering department. My faculty mentor this summer was Professor Kareem Owais, and my postdoc mentor was Narayan. The OAS lab is very interdisciplinary, conducting research in neuroscience, systems engineering, and translational neuroscience. The OAS lab is interested specifically in investigating the neural mechanisms underlying sensory motor integration and how they can be used to guide brain-machine interfaces clinically. Additionally, the OAS lab uses deep brain stimulation to activate mechanisms in the brain using a closed-loop system to potentially treat a variety of conditions, including Parkinson's disease. In order to discuss my research for this summer, I will give you some background on Parkinson's disease. Parkinson's disease is a neurodegenerative disease that affects dopaminergic neurons in the midbrain, specifically the substantia nigra. Dopamine moves from the substantia nigra to the basal ganglia through the dopaminergic pathway. Therefore, people with Parkinson's disease have low levels of dopamine in the basal ganglia, the structures involved with movement. This causes Parkinson's disease patients to experience tremors, rigidity, and slowness of movement, also called bradykinesia. Not only is there the dopaminergic pathway from the substantia nigra to the striatum, which disappears in the Parkinson's disease classical model, but there are also direct pathways using the D1 receptor and indirect pathways using the D2 receptor that are largely abundant in the striatum and therefore play a role in the movement of dopamine around the brain. For this project, we wanted to create a Parkinson's disease mouse model that is specific to dopamine loss in the basal ganglia while keeping dopamine intact in the cortex. To achieve this objective, we targeted the D2 indirect pathway in the basal ganglia instead of the dopaminergic pathway, which is usually targeted in the classical model. In order to do this, we crossed DRD2 LOX-P mice, which carry the conditional DRD2 alleles in homozygosity, with mice called Adora 2A Cre that express Cre recombinase in the striatal medium spiny neurons that denotes the indirect Parkinson's disease pathway in heterozygosity. The offspring of this cross is 50% indirect medium spiny neuron D2 knockouts, also called IMSN D2KO, and 50% control heterozygote littermates. This mouse line will exhibit bradykinesia while showing normal dopamine release properties, thereby affecting dopamine deficiency only in the striatum to give rise to a Parkinsonian condition. You can see that there is notably less DRD2 mRNA in the knockout mice. Before beginning experiments imaging cortical activity, it is important to study the animal's behavior in the regular environment by studying and quantifying its locomotor behavior. We created two basic tests that would fundamentally quantify the deficits seen in the mice. In the open field test on the right, mice are put in a novel environment and tracked over a period of time. Their distance traveled is then calculated using a MATLAB code that I created. In the grid walk test on the left, mice are put through the bridge in order to analyze their balance. Once these deficits are quantified, we can then begin imaging cortical activity in order to map the cortical dynamics in a Parkinson's disease mouse model. The parts of cortical imaging include imaging the mouse during navigation in a virtual reality environment, then imaging when stimulating the areas of the brain that regulate the basal ganglia. Lastly, I would like to say thank you to the University of Florida for hosting this program. Thank you to the provost, to the mentors, and everyone involved in making this program successful. I also wanted to thank Mike Nazareth for organizing this program and always planning fun events for us to attend. And I want to thank the OAS Lab for investing time to teach me throughout the summer. You guys have been amazing, and I will forever be grateful for all that you have done. Thank you to anyone I forgot to mention. This has been a wonderful opportunity.